This source code is a simple marble toy demo created using Matter.js and p5.js. When you click, a marble is added at that position and it interacts realistically with obstacles in the ground. Matter.js handles the physics calculations, while p5.js takes care of rendering and user interaction. One key point is that the obstacles are tilted, allowing the marbles to roll down naturally. Additionally, marbles can be added interactively with mouse clicks. This code serves as an excellent sample for beginners to learn the basics of physics engines, offering a concise experience of what Matter.js can do. Looking ahead, this project could be expanded into pinball-like games or puzzle-style applications where marbles pass through mechanisms. Since Matter.js also supports constraints and collision groups, it can simulate more complex systems and interconnected mechanics. Thanks to its compatibility with p5.js, it's also well suited for artistic expressions and educational visualizations. Let's take a look at some core physics engines written in JavaScript. Plonk.js is a JavaScript implementation of Box2D with a rich API, ideal for game development. Omo.js is designed for 3D physics and is lightweight, often used in conjunction with 3D. Rapier.js is a modern engine written in Rust and compiled to WebAssembly, supporting both 2D and 3D. Omo.js is a WebAssembly port of the Bullet engine, offering realistic simulations but with heavier performance demands. Among these, Matter holds a unique position. It is a fully pure JavaScript engine, which makes it the easiest to integrate into web environments. It has no external dependencies, a readable code base, and is excellent for learning purposes. Its API is simple, balancing realistic physics with usability and performance. While it may not match the precision or speed of other engines, its value lies in experimentation, prototyping, and education. Finally, let's summarize the key calculations involved in a physics engine. First, Newton's second law, F equals ma, is used to derive acceleration from external forces, which is then integrated over time to update velocity and position. For collision detection, the engine determines whether two bodies are in contact and calculates the normal vector and penetration depth. Calculation response involves recalculating velocities based on restitution and mass, following the law of conservation of momentum. Friction and air resistance are modeled as decelerating forces opposing velocity. Rotational motion is also considered, using torque to compute angular acceleration, which updates angular velocity and orientation. In the case of constraints, the engine applies corrections based on specified relationships between objects. These physics calculations are performed dozens of times per second, enabling a surprisingly natural simulation of the real world.